All, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore, and in this December month lecture series, we are going to discuss about modeling of biological systems. And here I have chosen the topic regulation of ventilation. And in normoxic conditions, breathing is controlled almost exclusively by the level of CO2 in the arterial blood. Ventilation is highly sensitive to PaCO2, the partial pressure of CO2 in arterial blood. A rise in PaCO2 by 1 mmHg from its normal level of approximately 14 mmHg may increase the ventilatory output by a third of its resting level. However, upon ascent to altitude or during inhalation of a gas mixture containing low O2 content, there is an additional drive to breathe due to hypoxia. This hypoxia drive becomes noticeable when the partial pressure of O2 in arterial blood PaO2 drops below 70 mmHg. Here, once the metabolic consumption rate of O2 and the metabolic elimination rate of CO2 are relatively constant in the steady state, a higher level of ventilation would lead to an increase in PaO2 and a decrease in PaCO2, which is in turn would lower ventilation. Okay. See here the first diagram, respiratory controller and lungs. Here we have VC, VE, PaCO2 and PaCO2. Here we have for input side and output side. Same, we have PaCO2 at the input and VCO2, and here we have VE, VA, VD. In terms of VD, VA and VE, we have represent the respiratory controller and lungs for regulation of ventilation. See, the operating characteristics of gas exchanger are obtained by deriving a mass balance equations for CO2 and O2. We assume metabolic CO2 production rate to be VCO2. This is the rate at which CO2 is delivered to the lungs from the blood as perfusion the pulmonary circulation. In the steady state, this must equal to the net flow of CO2 exciting the lungs in gas phase. The latter is equal to the difference in volumetric fraction or concentration of CO2 while air entering FiCO2 and leaving FaCO2. The alveoli multiplied by the alveolar regulation VA, the alveolar ventilation represents that portion of the total ventilation that actually participates in the gas exchange process. That's it. Okay. Here in this regulation of ventilation part, VA which is equal to VE minus VD and the CO2 mass balance VCO2 which is equal to kVA of FaCO2 minus FiCO2. Here the constant K allows volumes and the levels increased in BTPS units to be covered into STPD units. The conversion is achieved by using the ideal gas equation VSTPD 760 by 273 which is equal to VBTPS of PB minus 47 by 310. Here the above equation assumes body temperature to be 37 degrees Celsius or 310 K and saturated, and here the vapor partial pressure of 47 mmHg at that temperature. Here PB represents the atmospheric and the volumetric pressure under which the gas exchange process is taking place at sea level here. Here the volumetric pressure constant K which is equal to VSTPD by VBTPS which is equal to PB minus 47 by 863. Here the volumetric fractions FiCO2 and FaCO2 can be converted into their corresponding partial pressures PiCO2 and PaCO2 during Dalton's law. Actually, in this Dalton's law we have discussed earlier for cardiac input and cardiac output. Here PiCO2 which is equal to FiCO2 of PB minus 47. Here PaCO2 which is equal to FaCO2 of PB minus 47. Here the value of PaCO2 which is equal to PiCO2 plus 863 VCO2 by VA. Here PaO2 which is equal to PiO2 minus 863 VO2 by VA. See, The controller part of the system, which includes the chemoreceptors, the neuronal circuits in the lower brain involved in the generation of the respiratory rhythm, as well as the neural drive to breathe and the respiratory muscles. The controller response to CO2 has been shown to be linear over the physiological range. In the absence of vigilance, such as during sleep, the controller output falls rapidly to zero. And here, which leads to the increasing CO2 response slope as well as the ventilatory controller output. See, the formula is VC, ventilator controller output is given by 1.46 plus 32 by PaO2 minus 38.6 multiplied with PaCO2 minus 37, which is equal to 0. Here PaCO2 is greater than 37 and PaCO2 for less than 37. For greater than 37, Vc equal to 1.46 plus 32 by PaO2 minus 38.6 multiplied with PaCO2 minus 37. For less than or equal to 37, for PaCO2, the answer is 0. Thank you.